Thanks for the great introduction. Hello, I'm Sangho. I'm a postdoc researcher at Georgia Tech. In this talk, I'll introduce a branch shadowing attack. It's a new sidechannel attack against Intel SGX. This is a joint work between Georgia Tech and Microsoft Research. It's difficult to ensure that system software and hardware are robust against a sort of attack. So, if attackers have been successfully compromised some system software, such as operating system and hypervisor, they can access any sensitive memory content of user-level processes. Also, if an attacker has a physical access to a machine, they can do a cold boot attack to extract sensitive information from DRAM directly. Intel SGX is a technology proposed to overcome such security problems. It allows a user process to have an isolated execution environment called Enclave, in which even system software cannot access. Further, it automatically encrypts and decrypts data whenever that data is stored in or read from DRAM to prevent a cold boot attack. So far, no one has detected explicit attack against Intel SGX. But what about some sidechannel attacks? Recently, a number of researchers have proposed sidechannel attack against SGX that can reveal control flow and data flow from SGX. Some researchers have found that by monitoring page fault or by monitoring page access sequences, attackers can get page-level control flow without any noise. Also, some other researchers have confirmed that Intel SGX also suffers from cache sidechannel attack that can reveal cache line level control and data flow with some measurement noise. This is a simple example showing how a page fault sidechannel works. Here, an attacker wants to know whether a person is a member of some system by importing whether welcome or buy function was executed. If we assume that the three functions is member, welcome, and buy are located in different pages, we can know which function was executed by unmapping all memory pages and then monitoring page fault sequences. For example, if we observe some page fault at page 1 and 2, we can know that the person is a member of some system. Otherwise, if we observe some page fault at page 1 and 3, we can know that the person is not a member of the system. However, this attack doesn't work when these three functions are located in the same page because SGX only reveals page address, not exact address during page fault handling. Similarly, if a sensitive control flow changes occurs within the same cache line, cache-based sidechannel attack also doesn't work against Intel SGX. In this work, we propose a branch shadowing attack, which is the most fine-grained and sidechannel attack against Intel SGX so far. Branch shadowing attack can reveal individual branch instructions. This attack is not about which memory page or which cache line has been accessed, so we don't need to worry about control flow changes within a single page or a single cache line. Further, branch shadowing can deterministically identify each branch history. It can know whether a certain branch instruction has been taken or not taken, while doing not rely on any error-prone timing measurement. When branch shadowing also was able to recover, as an evaluation, we attacked RSA exponentiation within Xenon SGX. So branch shadowing attack was able to recover 66% of 1024-bit RSA private key from just a single run, implying that around 10 runs are enough to fully recover a 1024-bit RSA private key. Branch shadowing attack was studied from our observation. We observed that Intel SGX does not clear branch history during SGX mode switch. Modern CPUs cache how each branch instruction has been executed for later prediction to enhance performance. This information the information it maintains include whether a branch instruction has been taken or not taken, as well as its target address. Since SGX also maintains such information for later branch prediction, attackers would try to develop a reliable attack method to extract this information from SGX enclaves. Someone may think that why don't we use just performance monitoring unit, PMU, to profile branch history from SGX? Intel CPU has PMUs such as last branch record, LBR, process trace, PT, to that record each branch execution's prediction region as well as its target address for performance profiling. However, SGX has another secret feature called anti-sidechannel inference, ASCI. Because of ASCI, SGX doesn't publish any hardware performance event to PMUs to the SGX mode executions. As a result, malicious operand system cannot directly use PMUs to get SGX branches history. Then, do we have any other side channel to get branch history from SGX? It is well known that a mispredicted branch takes longer than a correctly predicted branch because CPU needs to do some rollback and re-execution. But obviously, we cannot directly time whether or not a target branch insertion takes long because it is inside of SGX. However, a recent work has found that colliding branch instructions that share the same lower bit addresses affect each other's prediction result. This is because their histories are stored in the same hardware entry to reduce some storage overhead. For example, branch instructions located at FF 1, 2, 3, 4, 5, 6, 7, 8 and FFC 1, 2, 3, 4, 5, 6, 7, 8 will share the same hardware entry for storing branch history. So if any of these two branch instructions has been taken, CPU will predict other colliding branches will also be taken when it attempts to execute that branch instruction. So we tested whether SGX also suffer from the same problem and eventually confirmed that branch execution inside SGX also affects colliding branches outside of SGX, which we named as a shadow branch. That is, instead of the actual target branch instruction inside of SGX, we can time a shadow branch to know whether the target branch has been taken or not taken. However, we found that this timing attack has actually have two critical limitations, making this attack less feasible and reliable. This timing attack suffers from some high measurement noise and has difficulties to synchronize target branches with each shadow branches. First, we compare the execution time of correctly predicted branch and mispredicted branch. On average, a mispredicted branch takes around 25 cycles longer than a correctly predicted branch. However, we observed that the execution time of a mispredicted branch is actually highly variable, whose standard deviation was around 800 cycles. This is because pipeline stall and rollback is a non-deterministic behavior in modern out-of-order processors. So this result implies that unless an attacker has a chance to execute a target branch multiple times to reduce some noise, each inference can be failed. Second, to avoid some branch history overriding, we need to time a shadow branch right after the target branch instruction has been executed. This is because CPU internal structure to maintain branch history are finite. For example, Skylake CPU's branch target buffer is a cache consisting of 4 ways and 1024 sets. Thus, in the worst case, 5 consecutive branch executions would override a target branch's history. However, because SGX doesn't allow a single stepping mode to avoid attacks, it's difficult to synchronize target and shadow branches. So far, I explained 2 limitations of branch timing side channel attacks. Then, how can branch shadowing attack overcome these limitations? First, instead of relying on error-prone time measurement, we use hardware PMU, LBR, against shadow branches to get branch prediction result. Note that SGX's security feature, ASCI, cannot prevent this attempt because shadow branches are outside of SGX. Further, this attack is deterministic because the LBR let us know whether a certain branch execution is correctly predicted or mispredicted. Second, to synchronize target and shadow branches, we realize near single stepping by increasing timer interrupt frequency as frequent as possible, as well as by disabling the CPU cache. By using both approaches, we were able to interrupt SGX enclave for every 5 cycles, which is almost the same as single stepping. So before explaining our attack in detail, let me briefly explain our SRAM model, which is very similar to that of the original control channel attack. First, attacker knows the source code and binary of a target enclave program. And second, attacker can frequently interrupt the target enclave execution to execute each proving code. Third, attackers can prevent or disrupt the target enclave from accessing a trusted time source. The branch shadowing attack consists of two steps. The first step is preparing a shadow copy of a target SGX program to indirectly monitor its execution with LBR. We have a target SGX enclave program consisting of conditional and indirect branch instructions. Because it runs inside SGX, an attacker cannot use LBR to monitor its behavior. Instead, an attacker can write a shadow code consisting of branches colliding with these target branch instructions and then execute it outside of SGX. Because this shadow code will be executed outside of SGX, the attacker can monitor its behavior with LBR. The second step is how we can synchronize the SGX enclave with the shadow code while monitoring its behavior with LBR. We first execute the SGX enclave and then interrupt its execution as frequent as possible. Then we execute our shadow code while enabling LBR. LBR will say whether the shadow branch's execution has been correctly predicted or mispredicted. Then we resume the SGX enclave again and repeat this obfuscation again to observe all of our target branch's execution. And note that whether or not the shadow branch has correctly predicted or mispredicted reveals the history of the target branch instruction inside SGX. Then, how can we write some shadow code for conditional branch and interpret its prediction result reported by LBR? This figure shows some detailed shadow code for a conditional branch. First, the target branch, conditional branch, and the shadow conditional branch have colliding addresses to make their history be stored in the same hardware entry. For example, we just make sure that their row bit addresses are exactly the same. Second, we make the shadow conditional branch be always taken by making the branch condition should be true, like comparing the same register to monitor each prediction result. We make our shadow branch works like this because LBR doesn't report any information about non-taken branches, so we make our shadow branch be always taken to monitor each behavior with LBR. Then we intentionally make our shadow branch be always taken. So whether each execution is correctly predicted or not depends on the target branch's previous execution history. So for example, if the target branch has been taken, CPU will predict that the shadow branch will also be taken because CPU will think that they are just the same branch instruction. And this is correct prediction because our shadow branch should be always taken. So LBR will say that the shadow branch has been correctly predicted. In contrast, if the target branch has not been taken, the CPU will predict that the shadow branch will also be not taken. This is actually a misprediction, so that LBR will say that the shadow branch has been mispredicted. Consequently, by using our shadow code and LBR, we can deterministically identify whether a target conditional branch inside SGX has been taken or not taken. Next, this figure shows how we can write some shadow code for an indirect branch. For an indirect branch, LBR report whether each branch target prediction was correct or not. So in our shadow code, we make sure that a shadow indirect branch jump into its default target, the next instruction. Since we use the default target address, our shadow indirect branch will be correctly predicted unless the target branch's execution update its cached destination. So if the target branch has been executed, CPU will predict that the shadow branch will also jump into the same destination of the target branch. Actually, this is an incorrect prediction, so LBR will say that the shadow branch has been mispredicted. Also, if the target branch has not been executed, CPU will predict that the shadow branch will jump into its default destination, the next instruction. This is a correct prediction, so LBR will say that the shadow branch has been correctly predicted. Consequently, by using our shadow code and LBR, we can deterministically identify whether a target indirect branch has been executed or not executed. Finally, to realize near single stepping, we increase timer interrupt frequency as frequent as possible and disable the CPU cache. we adjusted the timestamp value of the local APIC timer using a model-specific register, MSR IA32 TSC deadline. We give some value like 1,000 to this register to increase the time frequency as frequent as possible. So by doing so, we were able to interrupt SGX enclave for every P3 cycles. Also, we set cache disable read of the CR0 register to disable the CPU cache. By using both approaches simultaneously, we were able to interrupt SGX enclave for every 5 cycles, which is almost ideal to perform our attack. Okay. To evaluate our branch shadowing attack, we attacked a sliding window exponentiation of an RSA implementation, embed TLS. Embed TLS sliding window exponentiation has 2 branch instructions whose execution depends on I speed of the exponent. So by attacking these 2 branch instructions, we can recover 66% over 1024-bit RSA private key from a single run of an SGX enclave. That is, if we can run it around 10 times, we can fully recover the private key. Okay. Then let me show some short demo about this attack against RSA exponentiation. Okay. Okay. I first open our target code, and yeah, this is target code that I shows you guys just before. So we have 2 target branches whose execution depends on the I speed of exponent given to this function. So and this branch instruction will be executed if will be taken if the I speed of exponent is 1. Then I show the shadow code that will be executed inside of kernel. That is outside of SGX. So we just write shadow code within the Linux SGX kernel driver to do some simple jobs. And yes, okay. And actually, this shadow code has 2 conditional branch, the JNE1, 2 conditional branch, like our target branch instructions, and we make sure that this shadow branch should be always taken. Okay. Then this is how we can print the result of our shadowing attack. So because we use LBR, we just print LBR's result to the kernel debugger message, and we just watch the kernel log to observe the how LBR monitor our shadow branches. Then we execute our target code, and this one is exponent, the IC exponent we observe, and then this we can show that because we have 2 colliding branches, we observe some 2 entries of LBR, and according to I speed of exponent, we can observe that if the I speed of exponent is 0, because our target program should not taken. So, but our shadow code should say that we will be making always taken. So there is misprediction, and if the I speed of exponent is 1, this would be a correct prediction because our shadow branch will also be always taken. So by observing this, you can easily see that whenever there is IC exponent is retrieved, the LBR will correctly mention that there is correct prediction or misprediction. Okay. So far, I explained branch shadowing attacks in detail. Then, do we have any possible countermeasure against this attack? So we propose 2 hardware and software-based countermeasure against it. The first one is a hardware-based countermeasure that flushes branch history during SGX mode switch. We think that this is the most effective countermeasure but demand hardware modification. Also, each overhead depends on how frequently SGX mode switch will occur. We did a simulation to estimate the overhead of this countermeasure with the spec CPU benchmark and confirmed that the overhead is acceptable if mode switching frequency is not that high. For example, if SGX mode switching interval is around 100K cycle, the average overhead is around 2%. Since the timer intervals are generated once per every 1 million cycles in Windows 10, we believe that SGX mode switching per every 100K cycle is frequent enough. So we think that this overhead is acceptable. And the second thing is that we design a software-based mitigation to obfuscate branches. By modifying an LLVM compiler, we automatically replace a set of conditional and indirect branches with a single indirect branch plus a number of conditional move instructions. For indirect branch shadowing can only reveal when and whether it has been executed, so we can hide the branch directions. Also, we use conditional move instruction to conditionally update the indirect branch's target. We use mbench to check the overhead of our mitigation. Each average overhead was around 30%. And I explained how our branch obfuscation works with some simple example. This simple example shows how, yes, before the transformation, we can easily identify whether L1 or L2 has been executed by attacking this conditional branch. However, after our transformation, like the right code, we can no longer able to know whether this L1 or L2 has been executed because branch shadowing attack cannot know the destination of the indirect branches. This is possible because this Shih move instruction will be conditionally update the target register that our indirect branch will use. So yes, this is possible because of this Shih move instruction. But note that the attacker are still able to know whether the indirect branch has been executed. So the timing attack would still be possible. So in this talk, we introduced a branch shadowing attack, a new fine-grained and deterministic sidechannel attack against Intel SGX. Branch shadowing can reveal direction and or execution of individual branch instruction inside SGX. We also propose hardware and software-based countermeasure against branch shadowing, branch history flushing, and branch obfuscation. Thanks for your attention.
Go ahead. Hi, Petros Maniatis, Google Brain. This is very impressive. I was a little surprised that you chose a sliding window modular exponentiation to show this, since there's constant time, non-tight loop versions of that. So would that be also useful there, sort of attacking the branch prediction there?
Actually, there are many crypto algorithms that try to avoid some branch sidechannel attacks. So if some crypto algorithm that designed to use that kind of technique, our attack cannot be applied to that kind of crypto algorithm.
I mean, OpenSSL uses that by default. So
yeah.
I think that attacking a sliding window exponentiation is sort of like shooting fish in a barrel. But I mean, I'm sure it applies to code that I would write, for example, rather than the crypto people.
Actually, yes. Because, okay, yes. Actually, we want to emphasize that our target cannot not just about crypto algorithm, because actually there are many normal applications that use a lot of conditional and indirect branches, and that kind of program is not kind of some mathematical algorithm, so it's very difficult to avoid any kind of branch instruction. So in that case, we think that it's very difficult to write some general application without any branch side channel. So yeah, that's some of our another argument.
Sure. Okay.
Thank you.
Adil from IBM. So I have a two-part question. First is, in your attack, did you run the enclave in production mode?
Yeah, in production. Wait, we don't apply any kind of. We use pre-release mode to run our SGX enclave.
So it is my understanding that not production mode, right? Because you
pre-release mode disallow any kind of debugging attempt, so it's almost same as the normal hardware.
Though I believe, feel free to tell me if I'm mistaken. But I believe that in Intel manuals, they specify that if you do not run in production mode, some of the security mechanisms will not be enabled. They don't really precise which ones, admittedly. I think ASCII is probably one of them, although, as you explained, ASCII is probably won't be a problem for your attack.
Actually,
so is there a chance that, I have the feeling there is, but is there a chance that if you were to run it in production mode, that the results would be different? That the attack would not work?
I don't think so, because actually we apply our, we monitor our shadow code. Here. So actually, we monitor this kernel address space with LBR. That means that obviously it should not be inside SGX. So it's not about applying LBR against SGX itself.
Absolutely. Yeah, no, that part I got. But it's possible that they have another countermeasure, not for LBR, but for the BTB, that they put into place in production mode. One could guess, but we cannot know because there's no way of testing it.
Actually, we don't have access to production mode, so
exactly.
I cannot really say that. But actually,
we
also present this stuff to Intel guys. We actually visit the Intel SGX team and discuss about this result, and they said that this will work. So
it's valid, yeah.
Yes.
Okay, that's what I wanted to know. Thank you.
Yeah. Thank you.
Thank you for a nice talk, Yuval Yarom, University of Adelaide. I wanted to ask, Intel has a 2-bit counter branch predictor, so that would imply, I would think, that some of the branches inside the enclave will not change the prediction. Have you noticed that in the runtime, in your experimentation?
Actually, we don't know about that stuff, so yes.
Okay.
Yes. But anyway, all the stuff we tested works as we expected, but we don't know that kind of some special branches stuff. So, yes.
Okay, thanks.
Thank you.
Hi, David Gens from TU Darmstadt, Germany. You mentioned that there is this hardware countermeasure which would be possible, right, to flush the branch target buffer. Mm-hmm. As far as I understand, the branch target buffer is not that big, right? So there's like a couple thousand entries maybe. Mm-hmm. Do you think it would be possible to emulate this in software by creating an eviction set and doing that when you exit the enclave, for instance? That would not require any hardware changes, right?
To do that, actually, we need some kind of very good knowledge about how branch instruction actually mapped into the branch target buffer and branch history. But actually, Intel do not reveal any kind of this kind of what kind of hashing algorithm is used and what kind of mapping algorithm is used. So it is very difficult to write that kind of code inside of some user level process or kernel level process.
Yeah, right. I think you would need to reverse engineer this hash function. Yes. But I also think there was a publication on that. I'm not exactly sure.
Actually, yeah. That micro, the paper that we cite, the micro 2006. Actually, they found some. Actually, but their finding is just for Hyesoon CPU. But after the Skylake comes out, there are some branch mapping information also to be changed, so nobody knows about
it's per micro architecture, right?
Yes.
Yeah. Thanks.
Okay.
Any other questions? Yeah, I think the work is very interesting, but one thing I would like to point out is and the software defense, mm-hmm. and as you mentioned, and still leak out, just the position of the conditional jump, right? And for a typical crypto algorithm, they already consider many good crypto algorithms. Yes. They already consider timing attack, mm-hmm. and they're padding the different branch. And but originally the attack is end to end, looking at from the input to output, right? But in the current case, because you expose the branch, just inside the program, mm-hmm. so attacker can measure the timing difference between the branch. So I think if you need to fix the code to defend against this attack, the bar will be much higher. So I think maybe the hardware solution or other kind of solution will be a better way.
Yeah, actually, yeah, I agree with you some. But anyway, some crypto library or whatever in that case, writing that kind of code is somewhat easy, but there is some, if we want to write some code like printf or whatever, some very basic library, in that case, hiding that considering that kind of branchy stuff, right, and writing that kind of some very general program is very difficult, right? So.
Okay, nice. Thanks, speaker.
Thank you.
That's the end of session. Enjoy the break. Thank you.